Sorry.
Alright, hello. Welcome to my talk on template metaprogramming. First of all, I will apologize that it's not as good as I hoped it would be, because I suddenly remembered that we had a grant review today, so I didn't get that much time to actually work on the presentation. But anyway, it will also be too long. What can we do? So it works. Anyway, so the outline of the talk, we'll talk a bit about the basics. In the basics, I'll just write some simple programs that with metaprogramming, so you get a feel for how you. That's sort of the thing is metaprogramming has sort of evolved, so it's not as if you normally would necessarily write that boilerplate code yourself, but it's sort of just to get an idea of how you would go about it if someone asked you to implement something. And I'll introduce the standard metaprogramming vocabulary. In part number 2, I'll talk about templates are sort of cool, so we'll try. All right, so the basics first. So when writing metaprograms, there has sort of been this established vocabulary for how you talk about things. This was first introduced in the modern C++ design book by, I think that was where it sort of come from, by a C++ programmer named Andrei Alexandrescu. He's, by the way, a really cool dude. So if you ever feel like watching like a C++ talk, then his talks are really good. Anyway, so a metadata is basically any constant value that is accessible by calling value on any type. So in this case, this is just an example where it has some sort of value, and you can get that value by calling the namespace resolution operator. This is made somewhat easier with C++ template variables that we talked about last time, but we will not use them here. And there's a reason for that, and that's basically that, well, I'll show you later as well, but there's something about to have metadata work well with meta functions, you sort of want them to have a similar interface. So that's the next thing. No, this is also metadata. They're usually self-referential, so you also give it a type member type that refers to itself. I will also show you why we do this later. The next thing you have is a meta function, and a meta function is any function that takes its arguments through templates and stores the results in its type operator. So in this case, you, for instance, have an example of a meta function, and this is wrong. Sorry about that. This template should be here, because if not, then this wouldn't be correct, or this isn't correct in the way it's written up now. But anyway, because for this to be correct, we'd have to move this here, and this is an example then of C++ 11 template aliases.
Sorry, could you explain template a bit here? Because I'm
completely lost.
Yeah,
okay.
Yeah. So what's the template here?
So a template in C++ is basically any qualifier, I guess you can say, that you can give to a class or a function that can be filled when instantiating that object. That's a very complicated way of saying it. But basically any function, so C++ is strongly typed, right? So if I want to write a function that takes an integer and does something with it, I write a function and say it takes an integer. And then say I want a similar function that might take a double, and the content of the function is the same, but if you only had C, you would have to write one function for integer and one function for double. Templates lets you basically make this the type of this argument, a template argument, and that makes it so that it can be matched against any type it needs to be, and the moment it's matched against that type, it creates the function that it templates. So that's sort of what a template is. The thing is, templates doesn't have to be types. Quite often you think about them as types, but templates could also be numbers, characters, strings. Let's not get into that. And in that case, you could sort of say that the parameter you give it in the template sort of defines the type. So if I have a type that takes an integer as a template argument, then that type with template 1 is a completely different type from that type with template 2. Yeah. So
like an array that is long 10, an array that is long 11. This can be defined as two different types. And
yeah, exactly. So this is what a meta function is, and then you have a meta function class, which is a function object that can itself be treated as type, and the function call inside of a function meta function class is named apply. So in this case, the template thing makes more sense, because then you have a meta function class, which is just a struct, and it has a sort of a meta function inside of it that you can think about as apply. And the reason this is useful is because then we can sort of treat objects as functions in like the functional programming way of thinking. So this is all just vocabulary, so let's go to an example. So let's do some simple algebra. So here we have, first of all, like create this integer type, which just stores the value that it's given as an argument, or as it is template argument. And then this then would be a template meta function, where you see that the multiply is defined by its two arguments, and it gives back the result is stored in type, as I said. In this case, it will be an integer, where the value will be the multiplication of the values of the two arguments it takes. So if we now define a 5 and a -9, then we can have the result of this evaluation to be multiply of 5 and -9. We get out the type and we get the value from that. Following?
I think I need a few minutes on this slide.
So in this case, this is just a type integer 5, it's fine. This is -9 is another type of integer -9. These are different types, of course. So then we instantiate this multiply template class with arg1 to be 5, and 5 is integer 5, and -9 as arg2, which is integer -9.
Right.
And then we call type on it, and you see type here gives you the type integer, which is this, and the argument n for integer is the argument 1, and we take values. We take value of 5, 5 is integer 5, value of integer 5 is n.
Yeah, so right, okay. Yeah,
Does it make sense?
yeah.
Yeah.
Yeah, I mean the question why springs to mind, but I'm sure you'll answer that in a second.
We'll see. I'm not sure if I'll be able to answer that. But anyway. So, you know, as I said, that up there is metadata. The thing down there is an example of a meta function. And then we can also do a bit more. So say we keep integer as it is. Another way of writing multiply is by this construction here, where you basically inherit from integer. This thing has a special name, so this is called meta function forwarding. It's a different way of doing things. And this is one of the reasons it's useful for metadata to be self-referential, because the integer, if you call type on integer, you get integer back. So that means that by doing meta function forwarding and inheritance, then multiply is still a valid meta function, because it still has type. And type in this case will obviously be integer of whatever is in here. And this is an example of a meta function class. So say we have a functor that we call square, and square has an apply function, and apply is just calling multiply twice on the same argument. Or multiply on the same argument, not twice. And in this case, to call this and get the value of this, we can do square. We take the function inside of square called apply. We give it a type name, which would be the type in arg. In this case would be 5. And then when you fetch the value of this, then it's basically the value of this is stored in multiply. So that would be the value in multiply, but multiply inherits from integer, so it's the value in integer. Correct?
Okay, yeah.
Okay, good.
Okay.
So this is an example of just some simple algebra. So the thing though is that template metaprogramming has no variables. So this means that it is inherently a functional programming language, because that's one of the properties of functional programming languages, they have no variables. So let us implement something functional, like nest. So nest takes a functor, a argument, and applies it to itself 5 times, or n times. All right.
Right.
So in this case, we do sort of the same thing. So we create a nest function which takes 3 template arguments. It takes the function type, the argument, and the number. And you see that it's sort of very straightforward. So f has to be a meta function class.
Sorry, just you're using the word very straightforward.
Yeah.
Sorry. Anyway.
Sorry. So this is standard recursion, right? It calls itself again, and then we do basically this would be a template partial specialization that we talked about last time. And in this case, we partially specialize the situation where n is 0. And if n is 0, we don't apply the function at all, so we just return x. And in this case, you see that the type that we give it as x is just f applied to x. And then we call it with n-1. And in this case, if you do the same thing here, we do nest, and then we give it a function object, then we give it the argument and the types, and then we pick out type and value from this. We will get. We will basically say that type is applying a meta function, as I talked about, and then value you get the value of the application. Yes.
In line 4, what happens if you remove template from
so
before apply?
this is the problem. If you remember last time, I told you when you need template and when you need type name, right?
Mm-hmm.
So in this case, type name tells you that apply is a type, and not a value, and not a So in f, we don't know what f is because it's a template, right?
Mm-hmm.
So in f, we have something called apply. And the compiler doesn't know if apply is a type, or if it's a class, if it's a function, or if it's a value. So we provide this to specify that apply is a type. That's fine. And then secondly, apply also takes this, template arguments. And to us, reading this, we're like, well, it's obviously a template. But C++ still doesn't know this, because f is here. So if we don't say anything about this, C++ will assume that f apply gives you a value, and then it does the value of apply less than x larger than whatever.
Okay. It's the okay.
Right? So we have to specify template in here to make sure that it does it. I think I underlined one. So this is the thing you have to be a bit careful about. In here you see that we do recursion of nest. So nest instantiates nest. And then we have an end of recursion through this partial specialization. And so basically, if I write now a program that's 5 is some integer and the result is the nest of something, and then I compile this, then this is the machine code you get. So this number here is obviously 5 squared. And you get a little less if no one just clean up. And in this specific example, if you compile this with O0 without metaprogramming, then it does the computation as you expect. I think at O2 it managed to do this by itself. But this is obviously an example of something that's easy, right?
What compiler is this?
GCC 7.3, I think.
Is there any way to see? What happens in the with the templates without looking at the assembly code, or
No, what you
I don't know if there is any way to see some sort of intermediate C code that is produced or C++.
I think that debugging and things like that.
Yeah, of course, we want to debug to see what happens. Yeah, so to see what is. You need to be able to debug metaprograms, I guess.
Yeah. So the unit test of metaprogramming is basically used through static asserts.
Right.
And if you do a static assert, you can tell it afterwards, like a fail value, and then basically compiling your unit test is the same as running your unit tests.
Right.
There are obviously you could give your types names, and you could sort of have it print out the name of the expression recursively. If not, then Boost also has like a type pretty print that we could call on this, and it would basically convert this into the expression it is, and the expression this is a nest of square f on nest of square f on, right? So
Okay. But if you do, so basically do unit testing or die a horrible death are the two options.
Well, obviously,
you do test everything.
the whole point about, or the nice thing about metaprograms is that they run when you compile, right? So if you've done something wrong, your program won't compile.
Right.
Yeah.
Right. Yeah.
So in, like, obviously you could unit test some of the more heavier things, but I guess in general you don't really need to. It sort of depends on whether.
But you could have some logic. You know.
Yeah.
You could have some logic errors that would get through.
Yeah, and in that case you would unit test as you
Yeah.
do any other application, right?
Yeah. Cool. Wow.
So that's the short introduction to sort of how you think about and how you write these things. For the tools and library section, I started with, so I was looking at the previous talk I gave on metaprogramming, and then I gave the tools and library section using BoostMPL, which is the metaprogramming library in Boost. But researching a bit, BoostMPL was written for C++ 03, and it's just horribly outdated now, so we will not talk about BoostMPL. So let's talk about Brigand. So Brigand is a lightweight C++ reimagining of BoostMPL. So it basically just re-implements BoostMPL, changing some, because BoostMPL has containers for metaprogramming. So it has like vectors and lists and forward list and backward list and all of these things in metaprogramming. And the MPL people was sort of like, well, this is normally going to be short programs executed at compile time anyway, so like the difference between a vector and a list doesn't really make any difference. Like it doesn't matter. And because metaprogramming doesn't have variables, sort of appending things to lists and inserting things into lists doesn't make sense in the same way. So sort of the difference between, normally you would say, hey, if you want something where you can insert new elements in the middle, then you use a list, whereas for mostly anything else you use vector. But that sort of discrepancy doesn't really enter into metaprogramming because variables do not exist. So it has a lot of things. So it has like functional programming utilities, sort of the things you'd normally do when you do functional programming. It has sequence storage, it has sequence algorithms, it has various implementation of arithmetic operations, and a lot more. So first let's do our nest program with Brigand, because it simplifies things a bit. So Brigand has placeholders. So this means that we don't actually have to implement our squared function anymore, because now we could rather give it this multiply object, but instead of the two templates, we put in our Brigand placeholders. And then in the nest function, instead of calling our function apply, we call Brigand apply the function to x, and then it sort of takes care of all of the placeholders for us. And compiling this gives the exact same machine code as the previous one we had.
What's the difference? Sorry, you got the.
No, so the difference is it's not that much. I think I remind it. Anyway, so in this case, in the previous example, we had like a squared function that we created, which was like a functional.
Yes.
Yeah. And then in here we had the type name f apply template on x get the type.
Right.
Whereas in this case, we use the Brigand apply template function, meta function in here, which basically just takes any function and applies it to the argument, and you get the type from that. And then because of that, we can use these placeholders, which is sort of more of a lambda way of thinking about things, right?
I mean, nest is expecting a function as an argument, and you've just defined an inline function.
Yeah, so this is sort of like a lambda function.
Function as an argument when I've defined an inline function. When I say multiply.
So you multiply as a function that takes two arguments, you define a function that takes one argument to multiply 1 times 1.
Oh, I see what you're doing. Yes, okay, yeah, that's completely clear.
Sorry, so what does it replace the placeholder with?
So in this case, it replaces the placeholder with this argument here, right? Because the placeholder here, you basically define a type, and this is just multiply with the placeholder in these two places. And that's not a new type at all, that's something we have complete control over. But when this object will then be f, right? So when f is passed to Brigand apply,
yeah, okay.
then
Yeah,
it will fill in these and apply it appropriately.
I'm guessing Brigand also defines _2 _3.
Yeah.
Yeah, of course it does.
I see.
Is there a limit?
That's a good question. Oh, I remember I should have had a tweet on here. Someone sort of doing some problems with. So we'll get to const expr in a bit. But there is currently a bit of discrepancy in like the standard libraries where const expr is implemented or not. We'll get to it. But one of the tweets was like, in GCC, the number of arguments you can give a tuple is infinity, but it's also sort of 32, and 32 is much worse than infinity. But anyway, yeah, I guess there is a limit to the underscore. Probably. I haven't. I think so.
So if
What?
you say that it's closer to lambda.
Calculus. Yeah, because this would then sort of be a lambda function, right?
Okay, yeah, because yeah,
Because it's inline defined function.
inline defined with, and you've got no variables.
Yeah.
Yeah. Okay.
Does that make sense?
Yeah. That makes sense.
So Brigand can also do weird things like sequences at compile time. So here's like a type list, a Brigand list that like double short char int, and then you can create a new list that sorts, calling sort, on the previous list, and you tell it that the less than operator is the size of the argument. So this will basically give you a list that's sorted by the size of the type in this list.
Okay.
At compile time.
No, this is not okay. if previous one I could kind of, this is not okay anymore. Carry on here.
And
I can see where that could be useful if you're compiling for different architectures and they have different sizes of their types.
Yeah.
So, sort of probably the most insane use of metaprogramming I've seen so far,
Oh, I'm glad.
which I actually never did in here, but someone made a Json library in metaprogramming, which means that you can create a JSON string at the top of your C++ code, and then that could sort of be a configuration of your program, and then later you can do a at compile time check of the values of your JSON thing.
But you do all of this without variables.
Yeah.
I mean, this is what's mind-blowing, is you've got no variables.
No, but it's basically because
But
every time you do, like normally you would say, oh, if you sort something, you can sort it inline, right? You can sort a list as is.
Right.
Here that doesn't exist. You have to create a new list.
So yeah, so if I can have variables essentially, but essentially they're just sequences of constants.
Yeah, exactly.
Right.
And that's what I mean by not having variables. Like if you don't have variables, but you have named things.
Name things, constants that you can change.
Yeah, but you can't change the value of something. You have to define a new thing to apply your change. Like if you have x and you want to define x plus 5, you have to define y equals x plus 5. You can't do x equals x plus 5.
Yes.
So you only have constants.
Yes, you have constants.
Yeah.
But recursively, you could use recursion to do anything that you could have done otherwise, right? So I could say y equals, and then some series of some sequence of additions. Maybe if I want to do 10 additions.
Yeah.
I don't have to say y1, y2, y3.
No.
I
You
can
could-
use the recursion.
Yeah, sure, but you can't change the value of something.
No.
Right?
No.
So you can't do like a loop and add 1 to x at every stage of the loop, for instance. This doesn't exist.
You can't do a loop. No.
So the way you think about it, why you can do it recursively by doing multiple additions, that's fine. But I would say that's conceptually something slightly different from incrementing a value in a loop by taking the loop outside and giving you the end result.
Taking the loop outside.
Like
Right.
you can implement all the same things. That's sort of
But
the
you have
thing
to
about
think
like
differently.
functional programming versus like object-oriented programming and procedural programming. All of them have the same capabilities, but you approach problems in slightly different ways. Right? But yeah, no, the JSON thing is just mind-boggling because it's so cool that you can like have a C++ program and at the top you have like a string And in there you have like the configuration of your code, and then when it's compiled, the JSON thing just works. And at compile time generates the code given by the configuration you have in the JSON.
Yeah. So your code is always optimized for the one problem that you're running.
Yeah, and obviously you can do that anyway, but with JSON it's a more intuitive way of specifying configurations.
Easy.
It would save having to build a make system like we did with OpenGCD.
Yeah. The fun thing is I'm going to rebuild your make system. And at the time I was like, I don't like make, I really want to learn a different make system. But currently I'm reading a book on make, so that's obviously failing. But yeah. Anyway, I'll continue. So this is one of the examples of things you can do in Brigand. You can do a lot of things in Brigand. I didn't really want the talk to just be here are all the things you can do in Brigand, so if you're interested, look it up yourself. We also have Metal. I basically just did a search and looked at all the most popular metaprogramming languages and libraries and saw what they did. So Metal is sort of much the same. They do
This is a
Lambda.
different Metal from last week, right?
Did I talk about Metal? No, did you?
Last week? No, the video?
Oh,
yes.
That's a different
Sorry,
one.
that was a joke.
Yeah, no.
Sorry, yeah,
So this does lambda calculus in more the lambda calculus way, in the sense that the really cool thing about Metal, I was reading about Metal, and then they were like, yeah, we do bools as church booleans. And I asked myself, I don't know that much lambda calculus, so I had to look it up. Church booleans is basically by saying that a boolean is always sort of associated with a choice, and therefore Yes, and therefore a true value is always the first value, and a false value is always the second value.
You define your boolean by branch, don't you?
Yeah. So in this case, true type is the same as _1, and false type is the same as _2 for the placeholders.
You can build up, you can build crazy things just starting from there.
So that's in Metal. They also have type maps, which is sort of interesting. So they basically have a metaprogramming implementation of a map, which could be sort of useful because you could sort of say that if I give it this input type, it looks up in a map what kind of output type you want. I'm not saying it necessarily is. And Nest, if we want to do it with Metal, it's more or less the same thing. Here it's called invoke instead of apply. Down here it doesn't do like the placeholders as straightforwardly, so you have to do like a bind and a lazy. So lazy is obviously you give it something that takes template arguments and it doesn't necessarily fill in the placement or template arguments until later. But it does exactly the same thing. Alright, so let's talk about constexpr. So the interesting thing is we now have, technically speaking, there are two metaprogramming languages in C++ at the moment, because constexpr is a different way of doing compile time programming. So constexpr is basically a directive for telling the compiler that the following expression is computable at compile time. In C++ 11 we got constexpr values and constexpr functions. Unfortunately, in C++ 11, this was very limited. So it's like you could only have one return statement, you couldn't have branches, you could only have one line functions. It was a bit weird. In 14, they sort of removed all of those restrictions, which is good. And in 17, we got constexpr ifs and constexpr lambdas, which further simplify things because now you can basically have lambdas entering through constant expressions, which sort of highlights the functional programming nature of things again. So we can do the Nest thing again with constexpr. So if we first do it with constexpr 14, you see that we create a function that we define as constexpr, which basically means that if the argument is computable at compile time, then the result is computable at compile time. And then we create this Nest function in here, as usual, and this looks much more like a function because it's a function. So in this case, we tell it it's a constexpr function if all the arguments are known at compile time. The function thing in here is just so that I don't have to tell it that it's like a pointer to. Like function pointers are terrible, and the easiest way of dealing with them is just leaving it as a template argument and assuming you never call it is something weird, because it will fail to compile most of the times anyway. These are our universal references, which we talked about last time. So this is sort of to get move semantics in properly, to reduce overhead. Obviously, in this case, there are no overhead anyway, because it's compile time. And then in this case, it's just standard recursion, right? If n is equal to 0, return the value. If not, then nest it and apply f to the argument. And then you can put this into static assert. So it's compiled. With C++ 17, we got const_expr lambdas, which means that we didn't need the square function anymore. Now we can basically give it the lambda function for the expression, and it's still
Which is evaluated at compile time.
Still evaluated at compile time.
It's crazy.
So when you say const_expr as a function definition, then all of the function arguments have to be named at compile time?
Yeah. Yes. Well, no, not really. So the nice thing is that if you say something is const_expr, then it's a requirement that all of the arguments must be possible to compute them at compile time, but that doesn't mean that they need to be known at compile time. I'll give you an example. So there are a couple of like compile time constants, so like integers are compile time, doubles are compile time at 17, I think. Characters are compile time, these are fine. In the next slide, I'll actually talk about what. I'll just go there now, I guess. Makes more sense. So a const_expr is basically anything that only calls other const_expr values, or const_expr functions, or const_expr classes. And a const_expr class is something that has a const_expr constructor. So if you write a class and you write the constructor as a const_expr, and the arguments are all things that could be const_expr, then you have a valid const_expr class. Basically, it means that like vector cannot be const_expr. You cannot write a const_expr function that takes a vector because vector isn't const_expr. But if I write a function like the square and say it's const_expr, then that's fine. If I call it with like a runtime constant, that's also perfectly fine. It's not going to be evaluated at compile time, right? But the restriction is basically that all the arguments and all the things it does in the function body needs to at least be possible to do at compile time. So that means that it cannot create things that aren't const_exprs, it cannot do calls to new and delete. And it cannot call functions that aren't const_expr. It cannot do try and catch. I think they might be able to do that in the new. In 17, I think they added support for try and catch.
You're saying that they need to be something that's possible at compile time, but they can be defined at runtime.
Yeah. So they can be run at runtime.
They can be run.
Yeah. So it's a function where, if all the arguments were computable at compile time, it would be computed at compile time. But with one of the argument is computed at runtime, it will just be executed at runtime.
Okay.
Will it then create partial specializations or things if one of the arguments is known and the other one isn't? Compiling the known argument.
I don't think it will.
Okay.
So you can't do like currying type stuff, can you? With this sort of.
Well, I guess you could always. You could, separate things into multiple things and then combine them. Right.
Yeah.
All right. So we also got const_expr. So this is sort of just nice in the sense that, I very knowingly named my function will fail. But if you compile this, it will get a compile error because you cannot use a string for this function that takes an integer. And this thing will always fail for string, but it makes no difference because obviously every branch of a function has to compile when you compile something, right? That's standard, everyone. That's what you expect, right? But if you do const_expr in your if statements, then it still compiles because the falsy branch will just not be compiled because it's known at compile time that this if will fail. The other one was probably also known at compile time because of optimization, but with the const expr flag, you can tell it that this will be known at compile time. Are we all following?
Yeah.
All right, let's do expression templates. So first we need to talk about the ast. Would you say ast or ast? Do you have any? I don't know, actually.
I've heard AST.
Or AST.
Yeah, let's do AST. So are people familiar with ASTs? So it's just, we will see an example in a bit. So it's an abstract syntax tree, so it's basically a tree representation of an arbitrary algebraic expression. Or function calls on top of that, right? But we'll see an example. So with expression templates, we basically follow the exact same way as when we want to write like a lazy evaluation library. So we basically want to create an AST, and then we hook into it when it's evaluated to sort of determine what happens when it's evaluated. Does that make sense? We'll get there. So this is an example of what an AST looks like. So if you have this expression up there, then you see that the first thing that's evaluated is the minus operator. So it sort of splits into a branch where it's like, it's this expression minus this expression, and then to evaluate this expression, you split it into like a leaf, an operator on a leaf. Right? And then for more complicated things here, more complicated trees. So this is where my sort of my problem wanting to do everything in a perfect way sort of comes in. Because I asked myself while I was making this presentation, or while I was drawing this figure, because this is just drawn in text, I asked myself, why do I draw this figure? And it's obviously we want to show what an AST is. It's an essential concept in expression templates. So obviously the obvious choice is to write an expression template program in C++ that converts an arbitrary expression into this tree here. So this thing is generated by this C++ code.
Like this?
Yeah.
Okay. Where is code?
You're crazy.
What the heck?
So yeah, I don't know. So for this entire talk on my GitHub page, together with the talk, I'll have all of the source code for all of the examples in it, and the source code for generating these figures will also be in there. So yeah, it's sort of interesting, right? Write an arbitrary expression, there are these v's hidden around. This is, so basically in C++ 14 they introduced the option of having user-defined literals. So you know in C++ if you write like a number and an L, that tells you that it's going to be a long. If you write a number and then a dot or an F, a dot F, dot F, dot F, then it tells you that it's going to be a floating point number. In C++ 14 they introduced the ability for users to do this themselves, so define sort of the underscore operator. So in this case, the underscore v for me is a function I wrote to convert the expression to an appropriate leaf of my expression template tree. So basically this will be converted to the type that I'm going to use for my expression templates, and the same thing with this here. And then this is just a standard algebraic expression, and running this creates the figure on the previous page. Okay, so let's do like a first attempt. So this is obviously going to fail. Because you want to sort of start...
You think running that is going to produce...
Yeah.
There is a function called that.
Hmm?
There is a function.
Yeah,
There's a function here.
Yes, function call. So this is not a compile time thing. Expression templates are generally not compile time. Obviously you can have, like, the thing we will create after this is going to be compile time, because we have been going through. And I could probably get this to work with compile time. The problem is like there are strings in there and it's pretty horrible.
Okay.
Getting compile time strings is a lot of work.
You anticipated my question. Okay, cool.
Yeah. So obviously the people who did the weird Json thing implemented their own version of string that is const expr. but in my case I didn't do any of this. So this obviously runs at runtime, so this is not a compile time thing. The thing it does, I guess, which is sort of what you use expression templates for, is not really. So this talk is about template metaprogramming. Expression templates is not a metaprogramming tool. It uses templates to sort of get its desired effects, but almost all of expression templates is also obviously used at runtime. So the idea of expression templates is basically writing your code in like a syntax that makes sense and just having it do what you expect it to do. So in this case, obviously, what this here does is the thing inside of the brackets creates my AST, and then when I call to text on it, it basically parses the syntax tree for me.
Okay.
All right. So let's do like a first attempt, like what probably I did the first time I ever heard about expression templates and wanted to try. So in this case, we sort of create a plus expression, which is a type, and the type takes 2 arguments, and the result of it would obviously be integer with the value of the first argument of the second. This is sort of the same as the multiply function previously. And then we want to overload the plus operator, and in this case, we take 2 integers, and if you plus them, you get a plus expression back. And then obviously, if you do like your expression to be like 5 plus 8, obviously these need to be instantiated, because the syntax for not doing it with arguments is really ugly. Because obviously I could do like, here I could write the type of operator plus and fill in the template arguments, and it would be sort of the same thing. But the whole point of expression templates is to have something that's readable for anyone who reads this code. So you instantiate these temporary objects. The whole point is no temporaries are created during the expression, but that's still fine. And then we look at the value of this, and this works. We sort of have some problems here. So first of all, the thing I did on the previous slide, it doesn't do complicated expressions. Because if I write 5 plus 8 plus 5, then it will do 5 plus 8, okay, it gives you a plus expression, and then you have a plus expression plus an integer, and that isn't the same as that function signature, so that doesn't exist. So obviously a possible solution is you could overload and make like an integer and a plus expression and a plus expression and an integer, but we don't want to do that, that's really tedious. The other thing is it doesn't do. Another possible solution, I guess, to the same problem is that we could make our arguments in here more generalized. So we could say that, oh, we take any 2 types and then we create a plus expression. And this is sort of all right. The problem is, this matches absolutely everything. So this will destroy the entirety of our code, because if I now try to do string plus int, then normally C++ would fail to compile, but in this case, C++ sees, oh, there exists a template for plus that just takes everything, so let's use that instead. So you don't want to do that. And then obviously there's no easy way to like extend this to new operators and types. So if you want to do more of them, then possible solution again would be to overload all of them. But the number of combinations here is the number of operations cubed, so you don't want to do that. So yeah, these are sort of the problems that we have to overcome. So the time has finally come for the curiously recurring template pattern. All right, so what is the CRTP? The CRTP is a weird way of basically extending functionalities at compile time without having a vtable. So in this case, you create your type base, which is just fine, and then you say that it takes a template argument, and then your derived class inherits from base with itself as the template argument. So this is the curiously recurring template pattern. And the thing here is that if I now have a function called derived called, for instance, in derived, I can call it from base. So it's sort of an inverse inheritance thing, because now suddenly you can create a new function in the derived class and have the parent class call this. So in this case, you see that we do a static cast to like a t reference, for instance, where t is obviously derived in this case of the this pointer, and then we call derived colon. And the interesting thing is that it's a static cast, which means there is no vtable lookup. So there will be, like, as long as you don't make any other functions virtual, the curiously recurring template pattern will not have any vtable overhead, because this cast is done compilation.
Is this the ability to use the derived call, does it depend on the type that you instantiate the template?
Yeah, no, so the whole pattern is obviously that you do base with itself.
No, but the T type.
What do you mean?
The type of the first template.
Yeah. Obviously, if I do this with something that doesn't have derived call, you will get a compilation error.
I just don't know.
Okay. So I'm not sure
T
if
is derived.
Yeah, because this T is a template argument
So
of the base
if
class.
you try to create a class
Yeah.
with something other than type derived, a class base with something other than type derived,
Yeah.
you will not be able to use this function.
No, it will fail to compile.
The whole thing will go to compile.
Yeah.
Compile.
Your code will fail to compile because if you create something, like say I created derived and this function wasn't here, right? Or if I
can create it with
if I created derived and this was int, right? That's also fine, technically speaking. Then
Yeah.
when the compiler tries to instantiate this function call here, it will try to compile this and this won't compile. Because say this was int, right? Then t would be int, so it would cast a this pointer to an integer, and then it would try to call derived call on it. That doesn't compile.
Yeah, so it's not derived, it's things without derived call.
Yeah, and if you ever try to instantiate base with a template type that does not have a derived call function, it will fail to compile.
That's really neat. Do you write everything like this? I bet you do. Anything performance?
More and more, right?
Yeah,
because
right,
you can just
right. That's really
remove inheritance completely.
Really
It's also really generally just useful for adding like additional functionality to things. So say you want like, hey, I want like a generalized print operator or something like that. Then you can write a tiny little print class here, and then everything you want to be printable, you just inherit from it. It's sort of the standard object-oriented way of thinking about it anyway.
But you can't do anything that you can't do with object-oriented programming.
No, sure, but
Well, I mean,
but this obviously can be doable at compile time, something object-oriented programming.
yeah, no, I
can't.
mean, my question is, would you use this for anything other than performance? If you didn't care about performance at all, would you use this kind of pattern?
Yeah, I do it sometimes. I guess it's just, I don't know, for me sometimes adding, like say I want to add a single function to an object, and that function is sort of generic, and maybe that function even could take a template argument type, like a template argument. Then, so let's see if I can come up with an example. Say that I have a couple of classes and I want these to be printable somehow, right? And their sort of inherent value can be different types. So say it could be an integer or a float or like a string of a representation or something like that.
Inherent value.
Yeah, like say that you have like a class and it's like,
Okay,
if
I have
you try
something printable.
yeah, no, say you have a class and it's like you can do like a to something with it, like a to integer or something, and it's like the class has like a natural representation,
Right.
in
Yeah.
some sort of type.
Yes.
And I wanted to write a printer function that just calls sort of the proper to on it. Then I could have a printer function that uses the curiously recurring template pattern.
So each of these classes has a 2.
No,
No,
it doesn't.
okay, you want to add a 2. Yeah. Okay.
Yeah.
Cool.
Or it might have it sort of doesn't matter. But so say that my printer thing takes 2 template arguments and just not 1. So it's the curiously returning template pattern, but it has another template argument.
Right.
So the first one could be the template argument, which would be used in the CRTP. And the second one would be like an arbitrary template argument that sort of you tell it what kind of value it is for the printing operation. And then you can sort of hook in like an integer printer or a double printer or a string printer to lots of different classes without having to write an integer printer, a double printer, and a string printer separately, because that could be a template argument.
Okay, I may have partially
Understood what this
figured
does?
out what's on this page, but I'm still not. Well, if I'm not okay, so maybe I should just ask.
Yeah, go ahead.
What exactly does the second part do?
What do you mean the
It
second?
creates a new class
Yeah.
that is derived from the class base, which is actually a template class, so you have to give it an argument that it's derived.
Mhm.
That's fine. It declares that the class has a derived call
Yeah.
function. And because it inherits from the other one, it also has a base call,
Yeah.
which does some cast to
A T reference.
And T is now
Derived.
T has type derived, and it is T is a type.
Yeah, but it is derived.
It's type derived. Would you do some reference to a type?
No, so, okay, so say I'm in derived,
No,
right? It's fine. So say you're in derived. And normally, let's see. So normally, if you inherit from base, and assume that it doesn't have any of this template thing, and just assume that this line doesn't exist. Let's say that this is just an empty function, right? If you are derived, you inherit this base call function. If I call base call, then it will go to the type base, and then it will call base call. Base call is a member function of base, which means that the this pointer, in this case, points to a base type. Right? If I look at this pointer, in this case, it will be reference to base, or pointer to base. And in this case, this pointer is pointer to derived. Do you agree?
Sure. So you.
No, I'm not.
This is too basic. Just forget everything about templates even.
Yeah, that's what I'm
If
saying.
you inherit from another type and that from another class, and that class implements a function,
Yeah,
this, and then you refer to this,
yeah,
that reference will cast your object into the type base for the time being.
yes. It doesn't
Okay.
cast on it. It's basically,
It will sort of
Yeah.
it will
It-
work as if it was in type
Base.
of class
Yeah.
base, of type
Right.
base.
because this one doesn't know about the things it inherits from.
Yeah.
So it can't assume that it's derived, because it doesn't know derived even exists.
Yeah.
So in this function, this is a pointer to base.
Yeah.
So if we take this pointer and then we do a static cast so we also do references, so we get that references. And then we do a static cast to a reference of t, and t would be derived. And
Is it
since
possible to do this with just two types with no templates?
no, how would you?
The inheritance is going the wrong way around for that.
Yeah.
Silly question when he has a think. The derived. If I do this twice, if I had the derived class on the bottom, if that happened again, they'd have two different superclasses.
Well, what do you mean?
Well, I'd have two instances of the class. I'd have two instances of the class base,
Yeah.
not instance of the class, but I have two classes base.
So if I
and it'll
do
be
a second derived, then it will be based with the second derived type, and that is a different class. Yes.
so they can't share any. Okay, if I had any class level stuff happening,
No, so obviously
I
if you
can't
had-
get them to do this and share
No.
some unshared class.
No, it's well, sort of. Well, the thing is that basically the problem happens when you try to do regular polymorphism with it.
Yes. Yeah.
If I have a function that takes a base, then these two will not act both as the same type of base.
A function that takes a base.
That's what polymorphism would be, right? Say I have a function that takes a base, and then I can give it derived 1 or derived 2, and they can act as base.
Yes.
Yeah.
Yeah.
And in this case,
we're not talking template. Yeah.
no. And in this case, obviously, base would be different, so that wouldn't work.
Yes.
But you would normally write the polymorphism in that case using a template function. So it's
Yeah. But I can't combine two. I can't say, well, I want this, plus I want them to. No, I can't.
No. But that's why the CRTP
Unless I had. Yeah. Sorry.
is normally not really used for that type of polymorphism. It's sort of used to add functionality to something or to write expression templates, as we will get to.
Okay.
So what I was thinking was just that, when you're defining what you mean by your class base and you are implementing this function in there, but what you're saying is you cannot refer to another type if it has not been declared in the code yet?
Yeah, no, obviously. So what we could do is obviously we could say that it does no inheritance and no templates, right? Yeah. Or we could do inheritance but no templates. Then we could obviously declare define without defining it, and we can declare it up here. And then in base, we could say that we can cast the base to a declared type and then call something, and that would be fine. But the problem is, first of all, if you ever ran that with base itself, you would get a runtime error. Because you are trying to call something on a derived class when you yourself is actually a base class. So the static cast here will succeed, but it will give you something that's, like, it will basically just say that this is a bigger object than it actually is, and then on runtime it will fail. You could also do a dynamic cast, and the dynamic cast in that case would fail, because it's not actually the type, right?
Yeah.
But in this case, there's no dynamic casting. This all happens at compile time again.
But if you do it with inheritance?
Well, this is inheritance.
Without the template thing?
Yeah.
With inheritance?
If you want to do this with inheritance and get it right, you would have to do a dynamic cast here, and the dynamic cast could throw an exception. If you do not actually, if you call base call with something else than derived, so say you just create a base and do base call on base, and there's a dynamic cast in here, then the dynamic cast will fail. If you try to upcast, right? Because that's what, this is basically an upcast, sort of.
So this is, so it's somehow useful to be able to do this so that you can call base call with base.
Yeah.
Without templates, you would.
And I guess you will explain why that's useful.
So the standard use of the CRTP is, I suggest you find some articles on it. There's this blog called Fluency++, I really like, and he has like a series on the CRTP that does not talk about expression templates, because I introduced it here just to do expression templates. All right, are we good?
Yeah, we've got more questions, but I think we should probably move on.
All right, so let's do like the second attempt. Using the CRTP. In this case, I'll do it with pure types.
We've forgotten what first attempt was now. What were we doing?
Let's see, how far out is it? So it was this thing, right?
Oh, yeah. Right. Okay.
And then we had the problems where, this is horrible.
Okay, I remember the train of thought now. I've grasped it.
And this is 2, it matches everything, right? And
cool.
This is still tedious. Good. So this is the second attempt, and then we sort of use the ideas of the curiously recurring template pattern. So you'd say an integer, so you create like a base expression, which will be your CRTP base. And then you will say that your integer inherits from base expression using integer. And then you have your plus expression, which again takes 2 arguments, which inherits from base expression with base plus expression argument, right? So this is just the CRTP, it's just more templates everywhere. And then let's see. So this is basically the same as we did previously. This is not expression templates at all. This is just an example. Again, we can sort of create an integer from an argument. No, wait. Yeah, this is the plus expression. So this is the standard thing we did before, where this is the meta function, which just creates an integer with the values as arguments, and then its own value is given by the argument. So this is just the meta function we did previously. This is exactly the same as the multiplication we did. It's just that in this case I call it plus expression instead of multiplication or multiply, and it does this CRTP thing. The thing though is this is still pure types. It doesn't do anything with CRTP. So you can sort of forget it. I guess the second attempt is sort of borrowing the idea of the CRTP without actually using it. And then when we write our plus operator, in this case, you can basically say that it takes any base expression, any two base expressions of any arbitrary argument, and it returns a plus expression with argument 1 and argument 2. So in this case, I could do a static assert of a decal type. This is a C++ directive to basically guess the type of whatever is in here. And then we fetch the value of your decal type, and then we can do a static assert. So static asserts just means these are done at compile time. So you can sort of see that we've used the CRTP to limit the pattern matching. Because we wanted to do solution 2 to our problem, which was much more greedily, but we didn't want to be too greedy because then you break your C++ code. And in this case, we've sort of used this base expression with the CRTP to sort of limit that pattern matching. So this doesn't actually use any of the CRTP functionality. Base expression in this case is sort of just a tag. And so this would be sort of one way of doing expression templates. And I could sort of say that I'm done here. The problem is this obviously doesn't do what expression templates normally does, because this is a pure metaprogramming implementation of expression templates. Because you can't actually do any runtime with it. So if I wanted to have variables and say I wanted like an expression template for doing linear algebra, then we couldn't do it with this because there are no variables in here. So that's why we do the second attempt again using the CRTP. So in this case, we create the base expression again. In this case, we give it a member function called value, and value uses the CRTP. So you do a static cast, and then you upcast it with your CRTP static cast, and you call value on the thing that you upcast to. And then the integer class in this case would be sort of the same as it was previously, except that instead of having a value given by a constant, it now has a value given by a function. But this function is still const expert, so it's still compile time computable. Are we all right? Yeah, sure.
Curious about the distinction between const expert and const.
So const is just to tell something that something is immutable. Well, const expert tells you that it's compile time computable.
Does one not imply the other?
Const expert implies const, but not the other way around.
So why do you need const and const expert?
Oh, did I do? Oh, no. Sorry. This const is to tell you that the function is a constant method of your class.
It doesn't change the class.
Yeah.
The object.
Yeah.
Okay.
And I guess maybe that should be implied by the compiler, but in this case I think it failed to compile if I didn't. So, oh, maybe that wasn't the one that failed to compile. Maybe I don't need that const. I think I might not. Anyway, and then your plus expression is a bit more complicated. So in this case we store variables. So our plus expression will store constant references to the two argument types it takes. So we make a constructor for that. So this is very straightforward. The nice thing is we call our construction can be const expert, which means that the plus expression is a const expert class, which means that it's computable at compile time. And then again, we have this value function, which in this case just calls value on the two objects it takes. And the objects are obviously references to base expert, And when you call on that, it does the CRTP to get the value of the thing that it holds. And then the plus function, again, would basically look more or less the same as the last time, except this time we also need the actual references because we're going to construct something with these references. And then once again, we can do a static assert on any expression with a value. And this is computable at compile time. The nice thing about doing it this way is you're not limited to only things that are computable at compile time. So for instance, I used basically this. This is basically the way I wrote my expression tree figure program. I can show you that afterwards if you're curious. So yeah, simple. And I think that's the end of the talk.
So how would I use something how would I do this with something that's not compiled time compute?
No, in this case, it's basically you can, if you remove the context first for most of these things.
Okay. So could I do this with could I sort of could I use this to sort of partially apply and say, I've got some things that are compiled time computable and some things that aren't, and I end up with a function that's compiled with assumptions.
It sort of all comes down to how this apply function is, or value in this case, that was implemented, because this is sort of how you hook into your AST.
How far does the compiler actually go to evaluate this?
What you mean?
Well, I mean, in principle, if you add all your parameters to a computationally intensive application at compile time instead of in the parameter file, and make the mistake of writing everything as const expressions, the compiler could do your own simulation before. I assume that this.
Yeah, there is a limit. There is actually a limit. I can't remember what it is, but there is a limit.
Maybe that's relatively complicated things.
Yeah, the limit is very high.
But is there a limit more in terms of practical? You know, if I get everything to compute at compile time, would that be slower than potentially just running the code in the first place?
Yeah, no, obviously the compiler is slower at running your code than you are at running the things that you're writing.
Presumably the iterations are the key, so if there's something that's been done repeatedly.
Yeah, so most compilers have like a recursion limit, for instance.
What's compiler? Oh, no, okay. But I was thinking more about runtime iteration.
No, so you obviously want to apply these things in an intelligent way. So you want to basically compute things that make your, say you have some expression that needs to be recomputed a lot of times, you want those to be computed at compile time and just inserted, and then you obviously want to have it everything to be done at compile time.
Runtime, by the second.
Runtime.
Compile time. Cool.
How much would you need to add to make this into if you want to add just communication in there somewhere, if you want B to be taken from a different, you just make it a different type here and
and then you would sort of manipulate the value call in that type.
A couple of more lines.
Yeah. So thanks. So my talk is still up there, together with all the source code from all of this. I actually wanted the assembly also to be generated because now it's sort of, it runs the thing and computes the figures when you type make together with compiling the LaTeX. I also want the assembly to be inline, but I didn't have time.